Today's lesson is on the introduction to organic chemistry. When we talk about organic chemistry, it's a daunting field of chemistry that a lot of people hear that and they just psych themselves out to think, oh, I can't do that. It's really one of the most beautiful parts of chemistry. And when you get good at organic chemistry, everything else falls into place and you'll start to see things sort of make sense. It's like when you're doing a puzzle and you get to those last few pieces and they just fit in so nicely. Organic chemistry helps us to do that. Organic chemistry, when we talk about organic chemistry, everything is about carbon. It really is the chemistry of carbon and how carbon bonds. And because of carbon having a unique electron configuration, it has 4 valence electrons. Because of 4 valence electrons, it has 4 spots where it can bond to other things, allowing it to have hundreds of thousands of different ways that carbon can form different compounds. So carbon forms millions of other compounds in how it bonds. It's able to form hundreds of thousands of compounds with hydrogen. When carbon bonds with hydrogen, we call these things a hydrocarbon. And then when you add other groups to them called functional groups or alkyl groups, then you can have literally millions of combinations of carbon-based compounds. We are carbon-based life forms. Everything on Earth is. And it's the study of carbon, which is what organic chemistry is. Organic chemistry, the study of carbon, is how carbon can bond into long chains and rings, all these fancy compounds. And as you look down here in this bottom, you can see we can have carbon form into ethene, 2 carbons and a double bond. We can have carbon form into ethyne. Ethyne means it has a triple bond between carbons. We can have carbon form a 1 carbon chain, which is called a methyl. And then we have another group attached to it. We have methyl iodide. We can have carbons form chains that have an OH on the end. Now remember, in our acid-base unit, we talked about OHs. Anything ending in OH was a base. But I did mention that if you have C's and carbons and hydrogen there, C's and H's with that OH, it's not going to be a base. It's going to be an alcohol. This is the alcohol ethanol. So we have 2 carbon chain and the alcohol with it. We can have dimethylamine, propanone. It's all based upon how many carbons you have and then what's special in it. So it's naming things, sort of like an address. We're going to learn a whole new naming system. Here's ethanoic acid, dimethyl ether. You can have dimethyl ethyl ether. Oh, there's some great things we can do. So what makes carbon unique? Well, carbon is unique because it has 6 electrons. It has this electron configuration of 2-4, or when we look at the more complex configuration, it's 1s2, 2s2, 2p2. Now we know that everything wants how many valence electrons? They want 8. So this leaves carbon to have 4 bonds that are open for bonding with other things. So when we look at the electron dot diagram of carbon, since carbon has the electron configuration of 2-4, it means it has 1, 2, 3, 4 electrons in its valence shell, which means that reactivity-wise, we have room to react here, we have room to react here, we have room to react here, and we have room to react down here. So there's those 4 open spots. They're sort of like parking places that new chemicals can come in and bond to them. When carbon bonds, it has what is called tetrahedral geometry. That's a word you need to be putting into your notes. Tetrahedral geometry means it's forming this tetrahedral shape. You can see this pyramidal shape right here, where each of the hydrogens has a bond angle away from the other hydrogen at 109.5 degrees. So those hydrogens are arranged in a certain way. It's not perfect like when we draw our Lewis dot diagrams, we're drawing everything at perfect 90-degree angles. It's not that way in real life. When we look at the real shape, it is more of this tetrahedron with 109.5 degree angles. So, looking at organic compounds, they're used every day, whether it be in the aerosols in a spray can, in your bug spray, or whether it just be in things that we light on fire, because oftentimes these are very flammable substances. They go through combustion reactions. Our Bunsen burner, which we use in the lab, a gas stove in your house, those all burn methane. Methane gas goes through a combustion reaction, it produces heat. Methane is also what you pass out when you have intestinal flatulence. In a barbecue grill, you'll notice on your barbecue grill that down below, there's probably that tank that you've attached to it. That tank is a propane tank. Propane is a type of organic compound. Now, in methane, if you look, there's only one carbon. In propane, there's 1, 2, 3 carbons. So we have a longer chain of carbons in propane. In a lighter, we have 1, 2, 3, 4 carbons in the fuel that the lighter uses. Lighters, usually they are butane lighters, if you have one. This butane lighter is burning butane. Butane is a 4-chain carbon. So all those names were just determined by how many carbons were in the carbon chain, because in organic chemistry, you can just keep linking those together. They just keep building and building and building. When you were a little kid, you might have played with poppets or those things that stuck into each other and they made chains with them. If we were in class, you'd be using the molecular model kits right now. So carbon has 4 valence electrons. Its electron configuration is 2-4 that we would get from the periodic table. Having 4 valence electrons leaves those 4 places available to bond. Carbon forms covalent bonds with weak intermolecular attractions, meaning it doesn't have strong pull for other molecules of the similar thing, which means, since it has a weak covalent intermolecular attraction, that most of our organic compounds can be very easily put into the gaseous state because they have very high melting points, meaning they're going to melt at higher temperatures, and they have low boiling points. So they turn into a gas. They boil off from their liquid phase into gaseous phase at low temperatures compared to most other things, especially the ionics. And they're not very soluble in water. Organic compounds are often things like gasoline and things like oil, which, if you spill that in water, you're going to pollute the water by putting a slick on top. The water doesn't dissolve it. It stays there as sludge on that water. The intermolecular attraction, or the attraction between 2 molecules, that's what intermolecular means, between 2 molecules. The intermolecular attraction increases as the number of carbons increase. So in a 1-carbon organic compound like methane is CH4, 1 carbon, 4 hydrogens. If we were to add up in carbon how many protons and electrons it has, each carbon, it is atomic number 6. So it has 6 protons, which means it also has 6 electrons. So it's six magnets, essentially, between one methane molecule, and over here, there's another methane molecule. So it's like 6 magnets pulling at each other. So it's a pretty weak pull. If we go to propane, C3H8, there's 3 carbons in each of the propyl chains. So 3 carbons, each with 6 protons, means now we have like 18 positive magnets in our 18 protons, if you were to add them all up, and the 18 electrons. So now there's a little bit more pull between this propane molecule and this propane molecule. So these are going to have a stronger intermolecular force. In butane, like on that butane lighter, that burns C4H10. Butane has 4 carbons and 10 hydrogens. 4 carbons, each with 6 protons in its nucleus. If we were to multiply those together, you end up getting 24 protons. So it's like having 24 magnets in this butane molecule, 24 magnets in this butane molecule. So they're going to have more magnets, they have more protons and more electrons. That means they have a stronger pull. So what this means, and what you should be putting in your notes, is as you increase the number of carbons, going from 1 to 3 to 4 to 10 to 100 to 1,000. As you increase the number of carbons in a chain, you increase their boiling point. Now, why do we increase their boiling point? You increase their boiling point because there's stronger intermolecular attraction. Things with strong intermolecular attraction have high boiling points. Things with weak intermolecular attraction have very low boiling points, and they tend to turn into gases at a very low temperature, so they're a gas very readily. So the more carbons we have, the more intermolecular attraction there is, and because there's more intermolecular attraction, you have an increased boiling point. So some of the chemical properties of organic compounds. Organic compounds are molecular. Molecular, remember we talked about that earlier on in the year, is synonymous with anything that has a covalent bond. So they're molecular when we have things bonded, carbons and hydrogens, because it's non-metal bonded to non-metal. Things that are covalently bonded tend to react more slowly than things that are ionically bonded. So these are molecular compounds. They're made up of covalent bonds, and they tend to react fairly slow. Organic molecules undergo combustion reactions. Combustion reactions combine with oxygen as a reactant, and they produce carbon dioxide and water. So here we have methane. This is CH4. That's the organic compound. And that organic compound is going through a combustion reaction. And you always know the combustion reaction because you have oxygen as reactant. Your two products are carbon dioxide and water. Each organic compound has what is called a structural formula. This is how we try to represent a three-dimensional molecule in 2 dimensions. It's an electron dot diagram, essentially. So if you take carbon with 4 valence electron, hydrogen is 1, you can see that each hydrogen has an empty parking space where it can go and park itself, so that hydrogen has 2 valence electrons, and then the carbon has 8, which is the stable octet. Everyone's happy. So here we see our electron dot diagram for methane. When we draw a structural formula, every 2 dots, so every sharing of a pair of electrons, is actually represented in our structural formula as a bond. So a single bond is a single line. That's a sharing of 2 electrons as we share in this covalent bond. So the structural formula for methane, instead of drawing all the dots, we write it with the line structure. That saves a lot of time from the electron dot diagram. That's called a structural formula. So if we were to look at the molecular formula of this first organic compound, we have 1, 2, 3, 4, 5 carbons. So the molecular formula will be C5. And then if we count the hydrogens, we're going to find we have 12 hydrogens. So the molecular formula here, this is called pentane, is C5H12. So we have the molecular formula right here. We have the structural formula drawn out this way. And then we have what's called a condensed structural formula. These basically just tell you with the letters, the element symbols, how many you have in each spot. So we have, starting from left over here, we don't always have to start at the left. We usually start where there's a functional group or a double or triple bond. But in this case, since it's all single bonds, doesn't matter what side we start on. So we start with a CH3, 1 carbon, 3 hydrogens. So we've got CH3. That's written first. Then we have this carbon here, which has 2 hydrogens, and then another one with 2 hydrogens, and another carbon with 2 hydrogens. So then we have this section of the compound in the middle, which is made up of CH2s. How many CH2s? 1, 2, 3 of them. So in the condensed structural formula, the middle part is CH2 in parentheses 3, which means there's 3 of the CH2s. Then on the far side, the right side, we end up with a carbon and 3 hydrogens, so that would be written as CH3. So the condensed structural formula here is CH3, CH2, CH3. In this alcohol right here, this is ethanol. We look and we say, all right, what's starting on our left side? We have CH3. That's the CH3 right here. Then what do we have? We have a CH2. There's my CH2 written out. And then I have an OH. So this structural formula then can be condensed and simplified. And it's basically just an easier way to say like directions on a map. So we have a CH3, there it is. We have a CH2, there it is, and then ending it with an OH. Here we have a different compound. We have 2 carbons, we have 3 hydrogens, we have a 4th hydrogen, and we have a double bonded oxygen. So in this case, we say, what do we start with? We start with CH3. There's my CH3. Then we have what's else in the hydrocarbon here? We have a CH. And then to end it, we have this special group. We have this double bonded O. So the condensed structural formula is CH3CHO. So these are just the basics with how to begin drawing our organic compounds. In our next lesson tomorrow, oh boy, something to look forward to, we'll figure out how we start naming them and drawing them and how they all bond together. But the main thing you have to remember is organic chemistry is the study of carbon. And carbon always needs around it 4 bonds. It needs 4 bonds around it because it has 4 valence electrons. And those 4 bonds around it make it stable, giving it its stable octet. So we're always looking, does every single carbon have 4 things attached to it? Are we looking at 4 bonds around every carbon? That's going to be key to our success with organic chemistry. So that's it. I hope you learned a little bit today, took some notes, and I'll have a few assessment questions for you next.